This video is about an engineering fundamental. We use it a lot in fluids, but it actually applies to any subject that you've ever really worked with, and that is dimensional analysis. And although it's a little tricky at first, once you get the hang of it, you'll like it. And honestly, I think it's pretty fun because the goal is something that most students love, and that is to do as little work as possible. Do as little work as possible. Right now it's because we value our time and we'd like to have some free time. When you're at work, it's because time is money, and so the more time we spend on a project, the more it costs us, especially when it comes to things like experiments, or now that you've got some experience with the equations that govern fluids, you know they're very complicated and we often use computers to solve those. We call that computational fluid dynamics, CFD. And so we can do experiments, we can do simulations, all of which cost somebody money, and we want to spend as little as that as we can. And so let's introduce this topic here with an example, and then we'll get into the details in future videos. So what I want to talk about is designing a pipeline. This could be water, this could be an oil pipeline, whatever you like. When I say design, what I really mean is that we need a pump. Why do we need a pump? Well, shear stress makes the fluid not want to flow through the pipe. And so we have to overcome the shear stress, which you may remember we call tau wall. And we've shown analytically that this is related to the pressure drop and things like that. Well, we know that shear stress, or the shear force, the overall force acting on the fluid, depends on, wow, I can spell today. Depends on area. Which area? Well, the outer cylinder of our pipe, right? Not the cross-section area, but the surface area. That's where the shear stress acts. And so that area looks like a function of diameter and length. And so if we were being really efficient, maybe instead of saying what pump do we need for this pipeline, we could say what pump do we need for any pipeline. And so what I want to do is actually find the pump requirement per unit length of pipe, delta P over L. So this is the pressure that the pump has to create, and we can normalize it by the length here and say for any length pipe you just multiply by L and it would give us the pressure that you need from that pump. So this is the pump requirement per unit length of pipe. So now what I'd like to do is just brainstorm the things that might affect that. So let's think for a minute. Delta P over L. What are the things that this is a function of? Well, we already said one of them, right? The diameter. I'd say the length too, but we already caught that on the left-hand side, so we don't need it twice. The other thing that we're going to be interested in are the fluid properties themselves, right? If we go back and look at how we get delta P, remember 4 tau wall L over D, and that has a mu in it and a viscosity. So things that might matter include the density, the viscosity, and then if you change the speed, you probably need a different pump. And so the velocity at which we're trying to pump the fluid. Now, if we didn't know the velocity profiles and whatnot, we wouldn't necessarily be able to write down what this equation actually is. Right now it's just some unknown function f. And so one way we could handle that is to go out and do an experiment. In fact, the goal of most experiments is to change one variable at a time until we determine what this function is, because then we can use that to predict the behavior of any system. And so the goal of the experiment would be to change one variable at a time. Well, that's all well and good. We could conduct, say, 4 total experiments because we have 1, 2, 3, 4 variables that we're interested in. And if we did that, we could say do an experiment where we just change the velocity, and we could put delta P over L on this graph, and we'd get a couple different points from our experiment, and we could do some sort of regression analysis that would give us a curve. That tells us delta P over L as a function of velocity. But that's not the only thing that we're worried about. We've got 4 variables here, so let's do all of them. Maybe we also need to do, well, not maybe, we actually need to do delta P over L as a function of diameter. And so we go out and we conduct that experiment, and we get some data points, and maybe they look like this. And so now we're getting closer to knowing this function. We've got 2 of the 4 variables captured, and so real quick we'd go out and we'd do a few more experiments. One where we vary the density, delta P over L, and maybe that gives us some more data points like so that we could do a regression on to get this curve. And lastly, we do an experiment as a function of viscosity, delta P over L as a function of viscosity, and it's some other increasing curve like so. And so now, based on these 4 experiments, presumably we could fill in what this equation is. Here's the challenge. The way an experiment works is you change one variable at a time while holding all the others constant. Well, that's nice, and you could imagine here for the velocity how we might do that. You could speed up or slow down the flow in our experiment and measure these pressures and determine this. Same thing with the diameter. I could change the diameter and adjust a valve or something, and that lets me vary just the diameter without changing the velocity and measure this delta P again, and so that would be okay. The problem comes in when you look at the last 2. How might we change the density? Well, maybe we could change the temperature of the fluid, and maybe we could just change fluids, go from water to glycerin to maple syrup, I don't know. Each one of those has a different density. The problem is that usually if you change fluids, not just the density, but also the viscosity changed. And so conducting an experiment where we vary density without changing viscosity is really hard. And even if you try the temperature thing, temperature has a huge impact on viscosity. And so we got 4 experiments. The problem is the last 2 are more or less impossible for us to actually conduct. And so what do we do about it? Well, it turns out we can bypass this issue by collecting our variables into something called a non-dimensional group. So the fix to the problem is to collect the variables into 2 non-dimensional groups. So I'm about to teach you where all this comes from, but for now I just want to show you where we're headed. We got delta P over L. We take that and multiply it by d over rho v squared, and that is now some function phi, that's sloppy, phi of rho v d over mu. And you might recognize that's the Reynolds number. Really, this whole analysis tells us where that came from. What's interesting here is now I can make a single graph. On this axis I put rho v d over mu. On this axis I put delta P over L times d over rho v squared. And again, I go out and I vary this bunch of parameters, and I measure this bunch of parameters, and I get myself a single graph, a single function. And so this is really interesting magic that I've done. I've taken 5 variables and 4 functions, and I've turned them into 2 variables and 1 function. And when you say how, I say the Buckingham Pi theory, which is the subject of the next video. How? Buckingham Pi Theorem. Just to be really clear, what I'm saying is that for any fluid, I could vary this group of parameters and they would do what this graph says in terms of these. And when I said non-dimensional, what I mean is if you actually plug units into each of these two sides of the equation, you'll discover there are no units on these numbers. They're normalized, they're dimensionless. All right, so next video gets into the details of that.